My name's Andy Banta, and this is a portion of a presentation that I have prepared for Storage Developer Conference next week. I'm presenting it with a handful of other people, but this particular piece deals with CXL test drives. And I'm not going to go into a lot of history on CXL. If you're not familiar with it, there's loads and loads of Tech Field Day content on CXL. But one of the concepts of CXL is that you can expand the amount of memory a certain processor can get at any given time. So there's this concept that was built into computer architectures for quite a while, known as Numa. The idea is that it's non-uniform memory access. The idea is that not all the memory you're going to be accessing is right adjacent to the processor all the time. So originally, this concept was that if you had like a pair of CPUs, the DRAM attached to one CPU would be very adjacent, and the DRAM attached to a different CPU might have different access characteristics. CXL expands this idea with the idea that you can actually hang CXL memory off the processor as well. So instead of using a DDR channel, you would use a CXL channel, which is a slightly different protocol mashing on a PCI-E bus. And you can do CXL inside your box. You can do CXL outside your box over CXL connection. Coming soon, there will be CXL switches, and you can hang CXL off of these switches. And next generation switches will allow the switches to be shared among various different hosts. So when you're all is said and done, you end up 1, 2, 3, 4, 5, 6, 7, and some contention on all the various different ways, all the various different Numa nodes that you could access. In some cases, people are talking about putting SSDs in CXL, and that means that you have memory that's like 20 nanoseconds away right next to your processor, and you have memory that is milliseconds away, hundreds of milliseconds away, on an SSD outside of your box. So this means that you have very wide memory ranges, and the access times could be very different. But there's an awful lot of possibilities here, and wouldn't it be cool if you could go into your CXL dealer and say, here's my license and a credit card, let me take it out for a test drive. Wah. Sorry, you can't do that right now. An awful lot of these CXL devices don't exist yet, or just in conceptual phase. And for the CXL devices that do exist, it's very hard to buy them in the type of quantity that you would be meaningful to be able to test them. In terms of the switches, there aren't any commercially available switches yet, and some of the standards for shared switches are still being developed. So if we talk about the limitations of actually doing a real test drive, I mean, some of the things that you really can't test when you go to a car dealer is you can't take it on a long trip. You can't necessarily load it up with all the stuff that you would want to load it up with. And for those of us who care, lots of times dealers are in the middle of cities, and you can't take it out on a country road and tear around and figure out how well it's going to work. These are the limitations of test drive. With CXL, we want to get rid of some of these limitations. So the whole idea was that we wanted to be able to say, okay, we don't necessarily know exactly what application you're going to be running, but we're going to allow you to try various different workloads on a CXL environment. And we're going to allow you to actually run multiple workloads at the same time. We're going to allow this so you can do planning of where you put your data, how much data you need, how fast your interconnects need to be, the ability to change over time. And when you think about this, this all boils down to, this is what you normally do when you're engineering any product. You try out all these various different things, and you come up with the best choices based on the data that you gather from it. So this is one of the things that has been bothering me for quite a while. When you engineer something, you normally simulate it. And this is true of electrical engineering, chemical engineering, mechanical engineering, civil engineering, bioengineering. All of these disciplines use simulation to come up with the answers. And you do this because it's faster, it's cheaper, and it's simpler than actually building the entire system out. Isn't it about time that we did the same thing with software engineering and system design? So let's talk about how we would actually build a test drive. I am currently doing consulting with a small company named Magnition, and Magnition has built a large-scale simulation framework. The simulation framework is distributed, can be multi-processor, and it does discrete behavioral simulations of components. So the framework that Magnition has built, you can throw whatever components into it you want and run it and run applications against it. So you can choose a handful of different workloads that you want to have, and Magnition has the capability of running these workloads against the components. And the workload could be artificial. You could come up with just like a you can have a trace from an existing application, and you can run that trace against the simulation that you've built. One of the problems, especially with CXL, is that if you're running a trace, you're stuck with the sequencing that trace gives you, as opposed to having genuine sequencing that a CXL running application might have, an application that was running in CXL memory. The sequencing might not be right, and the trace is not necessarily going to give it to you the exact way you did it. You can do synthetic testing, so essentially hamster wheel testing, where you don't actually accomplish anything, you're just trying to exercise it to see what it's going to do. But what we've done is say, we actually want you to run your genuine application in a workload, and we have come up with a way of actually capturing the memory accesses that that application will make and trapping them all and being able to then say, these memory accesses are going to go to different locations. So on top of this, if this is a host in this case, all of these various different workloads would be attached to a memory subsystem, and this memory subsystem would decide how the memory is allocated, where what it goes to. So you have your local DDR memory. And typically on a current host, you'll also have a swap device as well, which will, in this case, we'll just consider to be an SSD. When we get to a CXL environment, we can also say that instead of just having a DDR connect memory, you can also have CXL connected directly to that processor. Or for future implementations, you can also have a switch out there, a CXL switch, and have what we call far CXL attached to that switch. So this is what we're hoping to be able to test drive, and this is what we've put together in our test drive, this type of configuration. So we have come up with, and this, I'm sorry, add a sequence here. I did want to point out, this is a fairly simple way to do this. What the various different components end up just being small functions that you can define as saying, this is what this component does, and you can piece them together as you need to. In addition, we have the ability to say, okay, there's a bunch of different things you can do here, and while we're at it, let's say that there's a bunch of variable things that you want to do as well. You want to try different configurations, and the simulation framework that we have will run through all of these various different configurations. So instead of plotting like 10 or 20 points in a graph, lots of times these simulations will end up doing millions of different variants to come up with exactly what's going on, and then you can take a look at the results, typically in a graphed form, and see where the sweet spots are, what factors make the most difference. And the kind of cool thing about this is that we also have graphical representations of it. This is not a CXL diagram because my cohorts haven't gotten that to me yet, and it will be ready for SDC next week. But the idea is that you have graphical representations, and each one of the components in it shows up as a box with all of the various different connections that go to other various different components. So this is important because newer processors, the newer enterprise processors from both Intel and AMD, have hundreds of cores, hundreds of PCI-E channels, and there's way more processing and way more I/O than you can actually use with local memory. There's just the amount of local memory you can put in a host would never satisfy that number of cores or that number of I/O processes. In addition, you end up with nodes that will have 8 or 10 or however, we heard examples from some of the customers yesterday of they were typically talking about nodes of 8 systems or whatever, which means that you're ending up with probably close to 1,000 CPU cores, and you need to have some way to feed those enough memory to keep going. So we just ran a couple very simple experiments, and again, since this is an incomplete talk, this will be nice and graphical next week. It's not this week. It was simply a description of what experiments I wanted for the engineers that I'm working with. But we start off with experiment 1, which would be no CXL exists, and we had 3 applications that had roughly the same memory footprint, but very different characteristics on how they use the memory. And it's like I wanted one of them to fit in the memory that's available, but 2 of them do not quite fit, and 3 of them to far exceed it. So the experiment we see here is that we have the 1 workload, the 2 workloads, and the 3 workloads, and you can see that as you add workloads, the amount of time it takes to run all of the workloads increases, and especially since we're using swap, which is horrible. So swap is way more laggy than CXL would be, because typically if you miss a memory access and you have swap, that process goes to sleep, waiting for that memory access to be satisfied by the swap system. That's not what happens with CXL with various different Numa nodes. For a second experiment, we said, okay, let's add some CXL to it, and let's say that we have some local CXL and some far CXL, and these are again just simulated bits that we've put together into the simulation. And we said, okay, let's treat all of this memory as just flat memory access. And the result here is that you can see as we add various different workloads, the overall time increases and the latency of the various different workloads varies somewhat as you start. These were the workloads were added individually, and you can see that as each workload is added, the ones that get added later get higher and higher latency, because those are the ones that are typically having their memory allocated out of CXL. So the way to handle this is that there's a utility that's available in Linux that allows you to choose which applications get which Numa nodes. It's called Numa CTL, amazingly simple name. And there's a variety of different options you can give it to tell it which nodes you get. So we reran this experiment where we said each one of the applications got a specific Numa node. And one of the differences you see here is that, yes, each one of the applications has a different latency associated with it, but the overall runtime for all 3 experiments is exactly the same, as opposed to when we ran it with inconsistent memory access, and as you added various different workloads, the overall runtime changed. And this is something that drives performance engineers nuts. If they try to run the same application more than once and the performance isn't the same, not a good thing. So this was just running through the various different experiments, and this was kind of the wrap up that I was going to do. The main point that I'm hitting on here is the last bullet point. The others are things that my other co-presenters are going to hit on more. But the idea is that you should be able to test drive your CXL system, and you should be able to do it in such a way that you end up with consistent results. And that is what Magnition is attempting to offer.